have to leave for a little while. Unfortunately, I have another thing I got to do. But then I'll be back and hopefully in time to see you guys out. All right, so let me just start with the recorder here.
Okay, so as Lee said, we're going to talk about AGS acceleration today, picking up from where we left off yesterday with AGS injection. There is a lot to talk about. The AGS is complicated, right? Heavy ion operation, polarized operation are different. And there are a lot of processes that go on that we haven't seen before, like transition and bunch merging and things like that. So there is a lot to cover. I may punt if there's a lot of interest in one of the special topics like transition or bunch merging. And we can talk more about it later in a different session and expand it because they deserve their own time in many cases. But first, I think we'll talk about, so this is the usual introductory slide, right? We're going to talk about the tools that are available to diagnose problems with the AGS, what signals are available to you, what instrumentation you have, and a general overview of the lattice, and this, of course, corresponds to another practical exam. So AGS acceleration, the categories are similar to the booster, right? You have the RF that does the accelerating, and then all of the magnetic elements, the lattice, that help you get from injection to flat top. The magnetic components are things like the main dipoles that provide most of the bending. In the AGS, we often refer to high field and low field magnets. The high fields are the big guys, the tune quads, the chromaticity sextipoles. The low things that are called low field magnets, we generally are talking about the orbit correctors, and in some cases the stop band correctors. But for our purposes, we're generally tuning orbit correctors more often. There's also a set of 6 quads, one in every other super period. They're pulse power. They're called the gamma jump quads, and we'll talk about that. They're to help us through a point of instability in the ramp called transition. And then, like I said, layered on top of the sort of AGS classic is all of this polarized proton stuff. So you need all of this to get through polarized protons with beam surviving and polarization surviving, plus a number of other elements that we'll talk about. That's another thing. I think later, closer to the run, we'll talk in more depth about polarized proton operation in greater detail when we can give it some more time. So here's just a brief peek at some of that stuff. And like I said, the RF system as well. So the AGS main magnets are powered by Siemens, right over at 929 in the middle of the AGS ring there. As I mentioned, the high field magnets, we're usually talking about the tune quad strings, there's a horizontal and vertical string, and the chromaticity sextipoles, again, horizontal and vertical string. There are also skew quads, which we don't often tune, but which are there, which are being used, and which can sometimes cause you problems. And it's one of those gotcha things where if they're wrong, it can take you a long time to figure that out, just because we don't often talk about them too much. And then there are the snake bumps, and snake compensation quads. So the snakes, right, there are 2 of them. I think maybe. All right, so we'll go through in the order I have. So our control over the AGS main magnet comes entirely from the AGS main magnet program, which most of you have probably seen. This allows us to load functions. The AGS main magnet is obviously PPM. There's only one user for the AGS at a time, right? Unlike the booster, just to say it once. So this is totally function driven. It uses all the same tools that we're familiar with. You can load archives and all that kind of stuff. And in addition to constructing the function, you can there's this tool under edit EFT to edit the flat top field altogether and the dwell field. And to set the flat top length, which again, we generally set once at the beginning of the run and then leave. It's not a source of downtime or anything. The high field magnets, we have control for them under AGS high field corrections in PET. So the power supply state control is all ADO driven, but the control over the amplitude is function driven, right? So we have this application called optics control for both the AGS and the booster, right? It's important that so over here is where you select which functions you're controlling. You select from the booster set, the AGS set, and then whether you're controlling tune or chromaticity functions, and then again, which one you're editing at any given time is controlled here with this horizontal or vertical selector. The other options are mostly the sextiles, drive sextiles and things like that. So one of the features that I think we probably don't use very often, but which is kind of useful under diagnostics up here, you can get readbacks of, so there are lots of things we can look at, right? There's the function we're actually sending down. We can read back what the controller thinks the function we sent down is, and we can read back an actual current. And those all get displayed on one window. Which is nice because when you can pull these signals up on a scope also, you can pull the currents up on a scope, but the scale is arbitrary, right? It can often be difficult to tell. You can't line up on the scope the function and the reference, the reference and the readback, the way you can with the diagnostic window, which is pretty useful. And another thing is that when you're loading archives, it's important to know this, I think, oft neglected window down here, or section down here. You know that you can control the functions in one of two ways, right? You can control it up here by editing the function, the current, directly. You can say, I want 50 amps in the quad supply, right? And the program will then calculate for you what tune it thinks you will get for that current. Alternately, and probably more commonly, we edit the tune. We say we want a tune of 8.8 or whatever, and the application will then calculate for you what current you need. So when you're actively editing, it's kind of clear what you're doing. When you're loading archives, on the other hand, it's not so clear. So this box here allows you to select whether you want to use, first of all, whether you're using the live main magnet function, or you want to look at the function as it was run. Okay, I'll explain that a little more in a second. Or whether you want to load the currents from the archive. You say, I want those currents, and then just calculate what tunes you think I'll get. Or you say, I want these tunes, and I'll give you these currents. It's important if you're loading very old archives because the quad configuration has changed, and so the relationship between the two is not necessarily the same. So in general, I think the safe thing to do, I usually select tune from current, right? If you want to go absolutely back to the currents as they were run, then you would choose current, tune from current, right? The reason there's a selection for VFT, right, is because part of this calculation is the main magnet function, right? In order to determine what current gives you a certain tune, you have to know what the energy of the beam is.
So when you grab this configuration of the machine, you load it, why would it matter whether you have current from tune or tune from current?
So the application doesn't know that at some point we wired extra quads onto the vertical tune string, right? It uses the same transfer function between these two.
Oh, so it only matters when there's a change in hardware.
That's the most important part. Yeah. I would say that's the only time I usually think about it.
Oh.
Right.
But you could have two other things, the main magnet field, but you would also want to click the main magnet field to use the one that has been archived, because it'll do a different calculation if you're using what's in there now. I make that mistake frequently. I mean, you think we haven't changed the main magnet function in the AGS for years, we use the same one, but we do change it. If somebody were to change the model, the numbers inside to try to connect currents with tunes because they're improving things, granted that hasn't been done very much, but don't count on it never having been done. That also would screw this up. So just being cautious by saying let's put in the currents that are there.
Right, it sort of depends on what you look for. If you want to set up and you know you want, if you're initially setting up and you know you want these tunes and you want the application to do the heavy lifting of getting currents for you, then you would load tunes and ask for the currents, right? But if, in our case, we're frequently trying to go back to a state when we knew the machine was running, right? And if you suspect that somebody has mucked around with this, you would say, give me the currents, right? I want to know what was in the machine at the time, right? And whatever you calculate for tunes, just I'm going to ignore, right? What I really want to know is that the machine is the way it was way back when. Okay. Anybody know what species this is? I like this question. It's hard to read, right? So this is 8.7, 8.8, 8.9, 9.
Gold.
Gold? going to be gold to protons, right? And I'm incredulous about gold because I don't know why we would run gold with such a high tune, right? I would want to be as far away from 9 as possible. Right, the only reason we run that close with is because of proton polarization.
Vincent, hang on, before we
Sure.
go, no, you don't have to even do that. I want to make sure everybody knows though, so in the booster, the main magnet power supply is connected to the dipole and the quads, one set of windings. Then the optics controls the tune supplies, which are extra windings on the same quads, right? In the AGS, the dipole and the quads it's a combined function magnet, right? So the main dipole is connected to the main magnet power supply, and that's it. This then controls extra power supplies which are connected to separate quads. Okay, that isn't a distinction.
Okay, so this is the application that we use to control the skew quads. You may even never have seen it. It's called AGS extraction, conveniently enough. So the extraction refers to slow extraction from the AGS, which we don't actually do anymore, right? These other tabs are pretty much exclusively for slow extraction, but this function lives, right? So this is the skew quad function. So this is the only thing we use it for. It's one of the reasons why you won't forget to check them in the event that you think that there's a problem. So it's worth mentioning. It's also worth kvetching, right? We should probably move this to optics control or something. Or at least call it AGS skew and use this as one function, which would be annoying. So that's the high field stuff. So if there are no questions there, we've done the low fields. So low fields, as I said, we're talking about orbit correctors and stop band correctors. So for our purposes, we're typically worried about the orbit correctors. For orbit correction and orbit distortions, we use two things, right? We use in the AGS, we use backleg windings, which are aptly named backleg windings this time, right? They're big C magnets, and I would be the backleg, right? The beam comes through here, the pulses are here, and the windings would go around my torso, right? I'm the backleg. And we'll talk about a couple of those. And there are 4 small dipole correctors per super period, and that's usually what we're talking about when we say orbit correctors, right? Meaning these low field guys, which are under AGS low field corrections, and they're arranged by plane, right? All the horizontal ones, all the vertical ones. So the state control, again, is in PET, and then the function control is in this application called AGS orbit control, which has a learning curve. There's no question about it. So the way AGS orbit control is arranged is by groups of correctors. So you've probably seen this at least a little bit. You go to bumps, select bumps, right? And you can get a list of the bumps that have been constructed, right? They consist of some number of orbit correctors, sometimes all of them, sometimes just a small subset. And then each orbit corrector has gains attached to it. It's terrible. So it's very difficult to see, but you can adjust the gain in each orbit corrector, and then there's one function for all the orbit correctors. So if you had a gain of 1 and a gain of half here, you would get the full current in one corrector, and half that current in the corrector would have a gain, right? And there are multiple gains in the chain, which is a little bit annoying. Somewhere over here, it tells you what the total is. So the ones that we're typically concerned with are these harmonic bumps. So they're designed such that as you go around the ring, the kick that you get is proportional to sine, for the most part, 9 theta for us, right? You would pick something that is near the tune you're running at because that's where you get the largest response. So the kick is proportional to sine theta as you go around the ring, and we can induce that kind of harmonic in the orbit. And I'm pretty sure I have a picture of that. Generally, we tune the harmonics rather than local bumps because at the higher energies, we don't actually have enough strength to put in significant local bumps with the low field correctors. But you do, if you use them all in concert, take advantage of the fact that you are between a tune of 8 and 9. This is particularly important for polarized protons, right? Because we're not just between 8 and 9, we're right up against 9, and so small dipole errors or small changes in dipole steering cause large increases in the harmonics. And so these frequently have to be tuned back down. And the polarization is sensitive to the values of these functions and some of the measurements of the orbit harmonics at certain points in the cycle, about which more later. So if you want to look at all this, we can use AGS orbit display. I think we sort of have shunned booster orbit display because there aren't a lot of pickups to look at. But the AGS actually has nice coverage. So if all of the pickups were working, we'd have 6 per super period, which is more than enough to get an idea of what's going on. So it takes some learning. Again, you should practice, right? This is totally non-invasive to be using this to look at the orbit at different points in the cycle. So you can be doing this all the time, right? It doesn't hurt the beam to check the orbit. And you should, because, again, this is it takes a little bit of learning to get to use this application effectively. There are lots of different parameters that you can set. So you can look at the orbit at multiple times, called scan times. So you can look at orbits throughout the cycle. You can average together multiple cycles. You can view saved orbits by setting these things correctly. Down here, you can select files from previously saved files if you like, and load old orbits, which is nice if you want to compare, right? If you're losing beam at some point and you suspect the orbit, you can compare to times when you knew we were running. Right, and you can do difference orbits, which could also be useful. In this case, we're just showing one time in the cycle. Anybody know what time, roughly? I say it because of horizontal, right?
Look at the orbits around G.
But even if I cover all this, right, somewhere here, it probably covers it. So this is 40 millimeters, right? So that would probably be bad most times in the cycle, right? So this is, this isn't, okay, not a fair question because you can't squat, right? This is G, this is H, and this is the middle of G and the middle of H, right? So this is G10 and this is H10, and that's the extraction bump.
One thing about this, by all means, play with it. But those scan times, if you change them, there's only one data set of scan times. So if somebody's actually using the application sitting over console 3, make sure you talk to them before you do it, because you will change the scan times out from under them.
Not to mention there's logging that is associated with
Right,
these, and you're also sharing the timing with the logging system, which is annoying. So it's fine if you're really doing things, but if there's a reason that we had the times set a certain way beforehand, it's nice to put them back the way you found them. Particularly for polarized protons, where we're concerned about drifts and injustice kind of thing.
So with that said, would it be always a good idea to just put it back where you found it once you're done
Yeah.
playing?
There's no plan to change that, is there?
I mean, the whole timing thing, certainly on the table, but we have to request it.
Yeah, right now it's in hardware. It talks to the.
That's what
It'll be good for the per instance of the application.
Like the loss monitor app, right? A different client. Similarly, so this over here, we really have to do something about this. You can't read it. It says graph, and in this case it says harmonics versus time. The other one says data versus location, right? So you were getting position versus location in the ring. In this case, you're getting calculated harmonics as a function of time in the cycle, right? So this is time from t0, and this is the amplitude of the harmonic in question, which are the orange is the cosine 9 theta, and the green is sine 9 theta. So rather than tune individual orbits at individual times, because these typically dominate, particularly for polarized protons, you can use the associated bump, right, in AGS orbit control, the sine 9 theta bump, for instance, to tune exactly this, right? You tune that, and in principle, you get exactly what you expect here. And you can move that, your knob matches your measurement in that case. It does frequently help to look at the actual orbits, though. If you have one bad pickup, for instance, one pickup that's reading like 35 millimeters, which happens, this harmonic, it just calculates it blithely, right? And it will tell you that things are a disaster, right? So you get, instead of -3 or whatever this is, you get -12, and then you can tune to your heart's content, but that pickup is not moving anywhere, right?
When we say the harmonic, does everybody understand what this is actually showing you? Right, the beam is waving around the machine, right? You can build a wave by adding up sine and cosine of different harmonics, right? So it oscillates close to 9 times, right? So there's a component of sine and cosine that's harmonic of 8 plus a harmonic of 9, and this thing just breaks it down for you. So with that wave, you get, well,
Those
if
are
these were taken at the
associated.
same time, right? You get, that is in time how strong the 9th harmonic is for sine and cosine. Right? So you're changing, without having to go in and change individual points on what the beam is doing, you can change different components of it. So if we're running close to 9, the 9th harmonic is a much stronger thing to look at.
So for much of this cycle, the orbit looks, at least in part, like this. Right, and this would be 2 millimeters here. Right, and you would have to add that to this other guy, this -2 in the cosine. Right, and the two of those get you pretty close to what the actual orbit is, in as much as these harmonics dominate. Yeah.
So if you broke the orbit up into its harmonics and you look at it on the application, you see that reading in millimeters, that what that harmonic component of the orbit of the beam, would that be the position? If you could take that beam and you're looking at it, you see it going back and forth in the machine, and you were able to break it apart, that component of it would have that position in the beam height? Is that what you're looking at there? Okay.
Right, so at this time in the cycle, right, there's an orbit component that goes like 2 millimeters times, which one? Cosine 9 theta, right? So that's one component, and then if I add to it the other guy, so this is -2 millimeters, -3 millimeters, -3 millimeters, right, times sine 9 theta, right? This is one approximation of the orbit, this is a better approximation, right? And the closer you are to 9, the better this is, because these are the only harmonics that can be excited, right? We could display other ones. It'll calculate 8 theta and 10 theta for you, right? And you can put those up, and then as much as you add those in, you get closer and closer to what you actually see on the previous plot.
Right.
No, I don't like any of these statements. This is just, if I give you a function, and I ask you to do a harmonic analysis of it, you can do it. You can tell me, okay, there's so much zero harmonic, which is the offset, right? And how much first harmonic, how much second harmonic, and that's all this program is doing. It's doing it there's another problem here that we have discrete points. We don't have contiguous points, so that I really choked in how I solved that problem that you won't notice it. So if I just tell you that to Fourier analyze a function, a continuous function, you can do it.
Yeah.
And that's all this is doing.
Okay.
So it's relative to, it's believing that the orbit positions are just the number. 0 is 0.
So I guess what I was wondering is, can you associate any physical placement of the beam to looking at these harmonics? In other words, when I look up there and I see that function's at so many millimeters, what does that mean, relative to the beam in the machine? What's that tell me, other than just some numbers at 2 millimeters, and it's good or bad?
It's 2 millimeters relative to 0. It's 2 millimeters.
All right.
So it's the beam is moving by 2 millimeters relative to the center of the pipe.
Okay.
With some little caveats there. How do you really know where it's at? Is the calibration really to know?
Well, I don't
But
wanna
the
get-
first order
I'm
of those
just
things are
wondering.
right.
Yeah,
Yes, the first
okay.
order of those things are right. So, yes, interpret it as if that was just the absolute value relative to the middle of the pipe. When you get on this kind of scale, like the horizontal extraction where you're 4 centimeters away, it's good. I mean, the errors in the system are not at the 4 centimeter level. So this picture, that's really what's going on.
Okay.
When you get down to tuning at the millimeter level, I don't know. I don't even know what a millimeter where the center is, but yeah, come to it as if it was right.
Okay.
And that's a good starting point.
The other thing is that polarized protons care about harmonics, right? The harmonics are important in a way that individual orbit locations are not, right? Kicks to the polarization can build up because you have this distortion in the orbit where they won't if you just had local orbit.
Yeah, okay, let's get back to this, as it is, this presentation is probably close to 2 hours, and now we've already spent 10 minutes on one slide, so. You can talk about it offline.
Okay, so so as I mentioned before, for polarized protons, things get complicated, right? So there are 2 helical dipoles installed in the AGS. Helical dipole meaning it starts like a dipole, and then as you go through it, the poles sort of twist, right? In fact, they twist in a complicated way in the AGS because there isn't a lot of space. But glossing thoroughly over that, right? There's one at A20 and there's one at E20, so that's a third of the bend, a third of the circumference around. We call them the cold snake. One is superconducting and the warm snake, which is normal conducting. They completely hose the lattice, right? If you turn the snakes on, you do nothing else, beam will not circulate, guaranteed. So to compensate for the effect that they have on the optics, they each come with these compensation packages. Each one has a set of 4 quadrupoles associated with it. So A17 is actually a horizontal tune quad that has extra windings on it for the purposes of compensating for the fact that the snake, which is nearby, is going to screw up the lattice. I can make a better picture of it. A19 and B1 are extra quads. They're these, if you go in there, there's these little skinny quads that are, sometimes we call them the thin quads. They're like just sandwiched in between 2 main magnets. And B3 is another pre-existing quad that has extra windings around it. These are around the cold snake, right? The cold snake is at A20. And then the warm snake has another set, E17, which is another, right, all the horizontal tune quads they're at all the 17, so they're extra windings around E17. There's another quad with extra windings at F3, and then there's another set of 2 thin quads around the warm snake. These guys are actually wired in series. That's what the plus is about. But one is positive and one is negative. One is horizontally focusing and the other one is horizontally focusing. On top of that, the cold snake requires an orbit. As you go through a helical dipole, wherever you go, so if this is the opening, right? Wherever you go through it, the beam starts on a helical path. So you go in and you start on a helical path. So as I draw this circle, I'm also moving into the board, right? So it goes around in a corkscrew like this. And this helix starts wherever you go in, right? So if you were to enter here, you would go around in a corkscrew like this. This is a poorly drawn picture, but the fact of the matter is that we use up just about all the aperture in the cold snake injection, so we have to be way to the outside of the cold snake. Otherwise, the circle bumps into the pipe on the other side. So there's this horizontal backleg winding bump. So it's a 3-bump, kinda, right? There's a set of backleg windings in series around these 4 magnets, and then there's a set of backleg windings around this individual magnet, and then another set in series around these guys. They're in series, but they're not all wired with the same polarity, so some of them go positive and some go negative. With the net effect that, right, at the cold snake, these are the A guys, this is A20, these are the B guys. The net effect is that the net effect is that we move to the outside of the ring, right? So the beam is going this way, counterclockwise. Right? So all of those elements, the compensation quadrupoles and the cold snake bump are controlled in this AGS snake correct application. And in fact, the cold and warm snakes are now controlled in this application, right? So you're probably familiar with it just from the much mode switched run we just had, right? So you have tabs for the bump, the cold snake quads, the warm snake quads, and then the cold snake and the warm snake are all controlled here. You can also get readbacks from over here or spawn GPMs that have these functions displayed in them. So this is a nice application in that you get both the diagnostics and the control there. You'll also notice that they're only really on early in the cycle, right? This is 200 milliseconds here. It's even before transition that they all go away. Transition's at about 300 milliseconds in proton cycle. The snakes are DC, right? So as the rigidity of the beam goes up, the effect they have on the optics goes down. By a nice trick of the math, the effect that they have on the polarization doesn't. So we only worry about these guys, and they should only be on early in the cycle, and they drop off very quickly as the main magnet begins to ramp. Okay, so the snakes are DC, right? We don't ramp them during the cycle. So for a given, for a fixed field, as the rigidity of the beam goes up, right, as we accelerate, their effect on the optics and on the orbit decreases, right? That helix that I drew, in fact, gets smaller. So if you start here, as the energy increases, the helix as you go through the snake decreases, right? And and eventually, near top energy, it actually looks like a drift. Right, because the beam is more rigid. Okay, so that is the very fast version of the AGS lattice. Right, the high fields, the low fields, and the snake components, and very handling terms. Okay, so in addition to that, we also have to accelerate the beam. So the AGS RF system has 11 cavities now. It has 11 identical cavities, right? Previously, we had talked about 10 cavities that were AGS cavities, and then the magical L10 cavity that was special and different, but it is no longer different, right? The physical cavity is the same as the rest of them. They have this funny non-standard naming scheme, right? We have the display, the Allen Bradley panel over on MCR1 that gives you state information. They're B, B, C, D, D, E, which is unlike the rest of the AGS naming system, right? Where we address it by the upstream main magnet, because there has to be an exception. So by default, the cavities can run at 12 and harmonics of 12 and 24, right? And we accelerate everything on harmonic equals 12. We capture gold from the booster at H equals 24, right? This is what we talked about yesterday, 4 transports, 6 bunches a piece. And so the AGS is completely full. Every bucket in the AGS is full, like Golden mentioned. Protons, we are at H equals 12 for the whole cycle. We capture the one bunch at H equals 12, right? The harmonic number doesn't mean you have to fill every bunch, and accelerate to the top and extract on H equals 12. The harmonic number for gold changes significantly because of the merge, which we'll talk about. The bunch merge requires extra harmonics to perform the gymnastics, right? This is where we take the 24 bunches and end up ultimately with 4, right? So we need extra harmonics to perform that gymnastics, so we have to dedicate some cavities. So usually there's one cavity dedicated to equals 4. That was historically always the L10 cavity, so it's the L10 cavity now. Previously it was the only one that could do it. And now there's another cavity that is usually configured to run at either 4 or 8. It runs 4 as a backup and 8 in normal operation. So that's the rundown of the high-level system, and then as usual, there's a low-level system that runs all these things, right? Provides the functions, calculates frequencies, and things like that, performs synchro, and drives the high voltage on those cavities. Similar to the booster beam control application, we have the AGS beam control application. Actually, not similar to booster beam control, right? So booster beam control we typically only use to control beam parameters, right? Injection frequency and that stuff. And we control everything else with Barfwig. This is more like Barfwig than booster beam control, right? So you control the beam parameters and the injection frequency for the AGS with this application, and you control the functions in all the cavities, right? So this is a proper RF application, unlike the weird hybrid thing you've got going on in booster. So you can adjust the RF cavity voltages, individual cavity phases. The radial steering function is available here. As I said, the beam parameters and the injection frequency, like the booster, you can set using this application. And you do it using all the usual interface features, except I will say that it's a little bit funny how you load and view cavity functions, right? So this bar down here tells you what cavity you're looking at, right? This is the displayed function. So in this case, we're looking at cavity B. Here, on the other hand, right, there are these open live and make live buttons. Here, make live sends it to any of the cavities that are checked up here, right? Which makes it easy to load the same function in every cavity if that's what you want to do. It also makes it easy to screw it up, right? If there's one cavity that shouldn't be like the others, which is typically true in, say, gold operation when we have these guys dedicated to the merge, who are only on during the merge and then go away for the rest of the cycle. So that's just a caveat when looking at these. Readbacks aren't available here for high voltage readbacks. You have to go into a scope. The radial steering function, much like the booster radial steering function, that's the controls for it anyway. A difference between the AGS and the booster. In the booster, right, the injection frequency is controlled by the beam parameters and radial steering, and then we accelerate on the frequency and phase loop. In the AGS, it's controlled by the injection frequency, it's controlled by radial steering and the beam parameters setting. The beam parameter setting is the major one, and then we view radial steering as a trim on that. For acceleration, though, we're on a radial loop, so we measure the radius, and there's a feedback loop that is designed to keep the beam in the center of the pipe as measured by these pickups. Right? So the pickups work because there are 2 of them, and they're separated by 180 degrees of phase advance. All that means, right, is you have two pickups such that if I have one of those waves, right, if I have a harmonic in the machine, if I have a dipole kick, if I have a dipole kick, right, these pickups are situated such that a kick from outside this interval here, right, will appear as negative, right, it'll be negative x at this pickup and positive x at this pickup, or the reverse, right, the sign is. The point is that you move equal and opposite at both pickups for a kick outside the region, outside the interval between these two pickups, right? The thing there is that if there's any change in the average measurement between those pickups, right? So kicks from outside don't change the average between these two pickups. So betatron motion, right, just regular transverse motion, doesn't affect the average value of these two pickups. So any change in the average reflects a change in the radius. So the view is to keep these by default at 0, and we can adjust where 0 is with the radial steering function. Right? That's essentially what we do with the radial steering. It's adjusting the target for the radial loop. Does that make sense? So we're on the radial loop for acceleration, and then we go off that when synchro starts. All right. So this could have a whole talk in and of itself, right? I'm just going to throw that out there. So we'll sort of go through this, and I don't want to spend another 20 minutes. All right. We can, is the thing, right? It'd be really easy to go off the deep end. So this is the first time we're talking about it, though, so we need to talk about it in some detail. So transition is a point in the acceleration cycle where the beam is susceptible to all sorts of instabilities, right? So just to complete, right, Travis' picture of phase space, I like how Travis got it. So Travis has been showing you, right, stationary. So if you're not accelerating, the synchronous particle, right, the guy at the origin should get no kick, right? The bunch should get a net 0 kick, right? You want to focus around this point, but you don't want the bunches to get a net kick, so you get this nice symmetrical picture, right, that Travis has been drawing, where this guy, who has the perfect energy and arrives at just the right time, when the wave is 0, goes nowhere, right? His energy and time of flight don't change at all. And the other guys who have errors rotate around, right? So in the accelerating case, accelerating buckets look quite different, right? Instead of wanting to be there, now you need, because the main magnet is ramping, for instance, to arrive at a time other than 0, right? If you arrived at 0, the net kick to the bunch would be 0, and you would spiral inward, right? So instead, you need to come up here, right? Everybody's got to get a positive kick because we need more energy per turn, right? And so what happens then is this bucket. So the bucket shifts, right? It's definitely smaller. It's not necessarily half the size, but it's smaller, right? The new stable point is here, right? This guy is the synchronous particle, right? So this bucket is smaller and not symmetric, right? Because now if I get a negative kick, my energy goes down, but there's still a stable region. The guys who get enough kick such that they stick around, right, they're still phase focusing, right? So these guys in here, there's still some stable region where I get accelerated just enough that I don't fall out of the machine between now and the next turn, or over the course of the next turn.
This is only below transition.
Right.
Yeah.
Right. So
Above transition, you want to be on the downward slope.
right. So that's the point. This whole conversation, right? All of these stable things depend critically on the statement that if I get a positive kick and I have more energy as a result, then I come around earlier, right? Positive kick, I come around earlier and get less of a kick, right? Because my energy is now closer to what we would ideally like. Everything we've talked about until now hinges on that idea. But there's a problem, right? Sooner or later the beam is relativistic, right? So down here where we live, below transition where everything makes sense, you get a positive energy kick and you move faster, right? But there's a speed limit. As you approach the speed of light, you can't go much faster, right? So there are actually two effects that are taking place, right? You're going a little faster and you are slightly more massive, right? And so as you become more and more relativistic, that bit that makes you faster necessarily gets smaller and smaller. For a given energy kick, your increase in speed decreases, but your increase in mass continues to forge ahead, right? And because you're more massive, as you go around the accelerator, you're going to take a longer amount of time, right? As you go through the magnets, you're bent less, and your path length increases. So below transition, where the path length increase, we'll say it's negligible, right? The speed matters, and this whole picture makes sense. But at some point, right, like I said, this mass gains on you. So at some point, for instance, you get a positive kick, and let's say your speed increases a little bit, but your path length increases by just enough to offset that, right? So now, despite the fact that you've gotten a positive kick, you come around in the same amount of time. So your energy is higher, but you get the same kick, right? You should have gotten less of a kick because your energy is closer to the synchronous particle, right? But you get the same kick. And on the next turn, because your energy is, your time of flight around the machine, your revolution frequency is still independent of your energy, you get the same kick again. So you move, so this picture doesn't apply, right? Because you move up and up, you come around at the same time, the same x value every time, but your energy increases and increases and increases. And sooner or later, you're at infinity, right, which is a couple of inches away when you're in a vacuum time. Right, so that point is transition. It's completely unstable. There's nothing new, there's no acceleration scheme where if you sat a transition, things would go well for you. Right? There are other problems. You're susceptible to all kinds of instabilities here, but the big deal here, right, is that you have to do something to the RF in order to be stable now. Because now above transition, it's going to be even worse. Because you'll arrive late, you'll get a positive kick, and now your energy is higher. And what actually happens is it takes you longer to get around, right? If you think about it in the limit where your speed is indistinguishable from the speed of light, right? If your speed didn't increase at all, but your mass increased, it would certainly take you longer to get around, right? And so now you don't just come at the same time, you come even later, right? And so now you're forcibly being pushed away from the synchronous particle, right? So this is what Chris was saying, is that what helped you before was this slope, right? That this slope was positive, that you got more kick the later you came, right? Because things make sense below transition. But what you need above transition is the reverse. So the synchronous phase now, I guess I didn't define synchronous phase. So I mean the phase on this wave at which this particle has to arrive, right? The design particle, right? Now what saves you is a slope that goes this way, right? For all the reasons I said. Now higher energy means it takes you longer to get around. So you should actually get the opposite kick relative to the synchronous particle. So this is called the RF phase jump, right? So this is a picture of just what I was saying, that the synchronous phase moves from here to here. This equation actually can't be right. These units don't work out. But the point is that you can calculate it by dV/dt is how much energy is related to how much energy you need per turn, right? How much energy the main magnet field changes. There's a relationship between that and how much energy you need to stay in the machine. And VRF, which is the maximum kick you could possibly get from the RF. It's just fact. You have to put like the charge on there. They both have to be energies.
That's supposed to be a curved equal sign.
Oh, okay.
We changed it from, okay.
Okay. Right, so this is what I drew before. You have to jump from the right side of the curve to exactly the same point on the other side of the curve, right? Because you still want the same net kick, right? The energy is still increased marching ahead at the same delta E per turn, right? So you want the same net kick, but you need the slope to be the opposite. So the RF has to jump very quickly to the other side of the crest. If you don't do this, or you do this at the wrong time, for instance, you'll get massive debunching, right? Depending on how close you are to transition. Right? This was the problem in Rick, in fact, where we weren't doing this at the right time. And consequently, we were blowing tons of beam out of the bucket, and then we would do the transition jump and have whatever beam was left. Because this always happens on the ramp, incidentally, all that beam is gone right away, right? So you'll experience this as beam loss. You won't see debunching, for instance. Okay, so that was the RF portion of transition in light, right? So one thing we can do, right, the point at which this happens is an energy, right? There's an energy at which we will satisfy this unstable condition. And you can calculate it from the lattice. I hand you an accelerated lattice, and you can calculate what energy this condition will be met, where a small increase in energy won't change your revolution frequency anymore. And that we typically call, we label it by the gamma at which it happens, right? Just the relativistic gamma. We usually call that gamma TR, the gamma transition. So you can calculate that for the AGS is about 8.5. You can also adjust it slightly by adjusting the lattice, which is nice because the faster you go, right, we're actually unstable for some period around transition. It's not just the point that's bad. The bucket gets bigger and bigger as you get towards transition, taller and taller. So as you get closer and closer, things get worse and worse for you. So you'd like to go through it and be done with it as fast as possible. Not to mention there's a spread of gamma in the beam. Right? There's a delta Q over P, spread momentum, so there's a spread of gamma. So not everybody goes through transition at the same time. Different slices of the beam will experience it differently at different times. So what you can do, we have these gamma TR quads. So gamma transition quads, gamma jump quads, gamma quads, these are all exchangeable terms for our purposes. And so they exist at every other, in every other super period at the 17 locations. And they're opposite polarities, they have alternating polarities. So they're in A, C, and so on. And they have alternating polarities. And the goal there is that they won't change the tune. Their effect on the tune should all cancel out, because things were nice and super period symmetric. That effect should all cancel, but they will affect this value called gamma TR, right? And so what we can do is if this is the beam gamma, the pink curve, which should track, right? If I blew this up, this is just near transition. But if I blew this up, it would look just like the main magnet ramp. And here, usually gamma TR is roughly static. But what we can do is we can ramp up these quads to adjust gamma TR up roughly parallel to the beam gamma, and then at some point, they're pulse power, right? So we just really crowbar them, we just short them, right? And they discharge all of their current. So on this time scale, this really doesn't look like a step. And then ka-chunk, the transition gamma comes right through the beam gamma, and this is transition crossing. And the crossing time is now much reduced compared to what would have happened if we were through like this, right? So that's the point of the transition quads. They don't dull any of the ill effects, they just get you through as quickly as possible. This is a view on the scope. This is the gamma quad ramping up over here and then discharging. And actually, it's faster than this would have you believe. Because these are 5 milliseconds, and this ramp down time is actually not as fast as they discharge. The other trace here is something called phase error. So this is what the RF thinks the phase of the beam is relative to the RF. And so at the point of transition, there's this momentary transient where we accomplish the flip. Right, so that's a good indicator of when the RF thinks transition is happening.
They don't really affect the tune, you said?
The goal is that they don't, that they all cancel out, right? The delta tune from a small chain, well, from a thin quad in a lattice, right, is like k times the beta function at the quad. So if one of them is positive k and one of them is negative k, all the way around the ring, they shouldn't have any effect on the tune. You'd like, right? If all the beta functions, it depends on all the beta functions being the same. And it depends on all of them being on and jumping at the same time, which is hard, right? That's it's a sharp drop. There's a GPM also that you can look at that shows them all at one trace. I think on that one, we need a reference. I think one of them is always easy. But right, that's the idea, is that they distort the lattice, but the tune stays the same. When you're really mucking around with the dispersion, you'd like to make the dispersion different and leave everything else the same if you could.
So the numbers say you don't see much of a tune change. Do we actually see more than would be predicted by the numbers, or what?
Question. So the gamma quad control, the state control and the triggering, these are triggered supplies, are all in PET. I didn't change this picture, but I showed it because this is like, they're all off here, and it's not set up properly. So these are start and stop triggers for the gamma quads. I'll explain. The gamma quads have a function, but it's triggered, it starts, unlike almost every other function that starts in T0, it starts from this trigger here, and then transition, as the RF cares about it, happens at this trigger here. You'll notice that all of them are Gauss time, right? Which is important, right? Because like I said, this is energy dependent, right? This is an energy at which the beam is unstable. And so if there's some jitter in the relationship between the main magnet function and real time, that would cause a jitter in this timing, which would be bad because the timing is pretty sensitive. And so we trigger off Gauss times. In that picture, incidentally, they were misordered, and all the triggers failed. So anyway. So there is an application called AGS gamma jump where you can edit the function. I would say we don't often do that. But like I said, the function is timed from those triggers, right? Not from T0, so it's relatively short. Other things that are going on in transition, sometimes people move the radial steering, right? Which is nice. You can move that relatively quickly, right? And that changes the energy of the beam also. So you sort of increase the speed by changing the radius. And there may be deliberate changes to the voltage going into transition and just after. Okay, so that's transition from the RF's point of view at laser speed. So this is, right, so I want to mention a few differences in the acceleration schemes that we use for different species. So for polarized protons, as I mentioned, we start cogs, sync to the booster, and then we accelerate, right? And we keep track of where the bunches are, where the bunch is, right? Because otherwise at extraction we would kick, and 11/12ths of the time we wouldn't have the bunch, right? So it's important to keep track of what bucket the bunch is in. And there's a rather elaborate scheme for doing that. So in that sense, polarized protons are easier for once, because there's one bunch, and all we have to do is keep track of it. For gold, we change both the bunch number and the harmonic number using this bunch merge thing, which I'll talk about in a second. And back in the day, we used to accomplish the bunch merge, the 24-to-4 changeover, with this debunch, rebunch thing, which we don't actually do anymore, but which is similar to like redoing booster injection, right? So as I said, we do this bunch merge for gold. We get 24 bunches from the booster once after the last transfer. And then we manipulate the RF harmonics. Started out at 24. We want to accelerate on 12, but we want 4 bunches at the end, which actually takes h equals 4, h equals 8, h equals 12, and h equals 24 to do this up and down dance. And the net effect, right, the idea is to take the original bucket. So this picture here shows the phase space, right, at different times, right? So the point there is to manipulate these. So you can think of the bunch as sitting in a potential well, right? The bucket is just a potential well. So what the bunch merge does is raise the barrier between, or lower the barrier between the two, so it separates these points here from the red curves, the initial curves of these blue guys, and then lets the bunches sort of spill over the separators into each other, and then we bring up h equals 12 ultimately, and they merge into one bunch at the end. So the way this happens, this is the first phase of the merge. It actually occurs in 2 parts. We start with 24, and we go down to 12 bunches in the gymnastics like this. And then we go from 12 to 4 in a 3-to-1 merge, which is shown here on the mountain range display, and I'll explain what I mean by that in a second. But these are, so this is the wall current monitor, right, showing you not quite a turn, right? So each trace is a wall current monitor. It's a wall current monitor trace, so each of these humps is a bunch, right? And you can look at the wall current monitor for some length of time, which you can set in the application. Typically it's a turn, right? And then some number of turns later, 1 or more if you like, you can lay another wall current monitor trace of the same length right above it, just stack them like that. So this is called a mountain range, some people call it a waterfall. So time goes like this. So the gross time scale, the long time scale goes like this. And a much shorter time scale, sometimes this is labeled in phase. If it's 1 turn, right, this would be 360 degrees around the ring. And so time advances, so this is a turn, and time advances like this. And so this is 3 bunches merging into 1 at the end. Right, the center bucket stays in phase where it is, and then the other 2 guys, it's very, very broad, and then the other harmonics are brought up to rebunch into the smaller buckets, into the smaller bunches. And this whole process is adiabatic, right? These voltages are ramped up and down, slow relative to a synchrotron period to preserve the emittent. Which means, by the way, that the end guys, the 4 bunches in the end, all have 3 times the emittance of the initial guys, right? Which is fine, but important to realize, because any more than that, we wouldn't fit in the right bucket. Okay, so right, so are there any questions about the merge?
And the thing to remember though, so you get 4 bunches when you're done. So this isn't a full turn.
Right.
You only see 3 of the bunches, 3 to 4. But then when this is all done, everything goes back to h equals 12. It's just that only every 3rd bucket is filled. Right? So we still accelerate our harmonic 12. So we use all 8 cavities that we can on 12 or 9. No, and that one switches 9. So there's 9 cavities that we accelerate on.
Okay, so just like everything else, it's important to really narrow in on what time in the cycle you're losing things. A lot of things are going on. Oh, where did the merge happen in the cycle anyway?
It's on the injection.
Right. So right. You have to get all of the transfers in. So anyway, the point is we transfer all of them, do the merge, and then accelerate. In my awful picture. Oh, but it's good that I have a picture because, so, we often talk about early acceleration, right? So there are 2 points that people sometimes refer to. One is B dot, which I think we talked about in the booster, which would be, right, the dot refers to dPdt, so that's when when the main magnet starts ramping. And then, for polarized protons in particular, we're concerned about this max B dot point, so this is the point where this curvature stops and you're in the main part of the ramp, where the B dot is maximum. And again, if you're looking on a scope at a narrow range of the main magnet function, this is not going to be obvious, right? If you look at the current, it's a relatively gentle slope. Well, it's an arbitrarily gentle slope as you look on smaller and smaller timescales. So there is a voltage function available to look at, and so when that is at a maximum, for polarized protons, it's pretty typical that you lose beam right here if the RF voltage isn't enough, right?
It should also be noted that problems with the merge don't cause a loss.
Yeah, that's a good point. So the merge usually shows up as a problem at extraction, right? And I talked a little bit about that, but since you brought up the merge well. So if the merge doesn't go well, the usual sign of that is there's usually a drift in the cavity phasing, and the sign of that is this baby bunch thing, right? So what will happen is you get to to extraction, everything's fine, but you extract to RIC, and the transmission efficiency, AGS to RIC, is arbitrarily low. Like, it could get as low as
what you're expecting.
right.
Depends on which one's out.
Depends on how it fails.
Right. If it completely
Right.
completely fails, you generally get a third of what you expected, right? Or
But you can
Either
lose
one.
the, you can
Yeah,
lose the
fail a
24
lot
to
of creative
12.
ways.
right. But it will look like, right, your first impulse will be to tune injection, right? To tune, say, apply V and apply H, and you can do that until you're blue in the face, but you'll find that you have an upper limit. And that's because the bunch merge didn't go well. And the only way to look at that is to look at the wall current monitor. So you can either set up the mountain range to look at the merge proper, but the easiest way to do it is to look at the bunches at extraction. And what you'll see there is that what you should get, right, what's good, is 4 equally spaced buckets. Edit, undo, right, 1, 2, 3, 4, right, 4 equally spaced bunches per turn, right. What you get instead, right, and they should be tall, proud bunches, but what you get instead is you get, remember, this is H equals 12 with 4 bunches, so there are buckets in between, so what you get instead is, and that beam can only come from this central bucket, so you extract these guys, but you're leaving behind being here. So if that gets bad enough, one way that sometimes appears is, if you look at the current transformer, right, come in, and then you extract all 4 bunches, you still have stuff left over that you see go away at the end of the main magnet cycle, right? So these are the 4, those are the, anyway, those are the extractions. You have extractions, and then you have something left over that goes away when the main magnet starts to ramp up. And that's, again, those are the baby bunches. Because these guys will extract cleanly. The ATR orbits will look beautiful. Your matching will look fine. Because everything is fine except that they don't have enough beam in them. If the cavity that does H equals 4 trips off and you don't notice, the merge pretty much doesn't happen, right? So you'll have something like 12 bunches. Rarely, I don't think you can get 24. I think you'll get 12 bunches. And so then you get a third of the intensity regardless of what you do. And the bunches look great, other than the fact that they're tiny. All right, so this is the rundown. So these troubleshooting things are, right, the whole thing is kind of a troubleshooting thing, right? Like, I explain a process and then we go through and we say, well, check all the things I just talked about. So very often, sometimes capture losses, so losses that appear, say, at B dot when uncaptured beam will die, right? Because the current transformer will see the D-bunch beam, right? If your injection matching wasn't good enough. And then that will die as soon as you start to inject. Transition, so bunching efficiency, transition efficiency, those are all dependent on longitudinal emittance. The bigger the beam is longitudinally, the more you have messed up earlier longitudinal transfers, the worse those can get. And that goes on down the line, right? RIC injection efficiency, and then RIC transition efficiency, and then RIC rebucketing efficiency, right? Emittance always goes up. So in as much as you screwed up the earlier processes, the later processes get harder and harder. So sometimes, and this is especially true in the AGS, sometimes you can fix things. I mean, keep this tuned AGS transition with like Linux cavity phasing, because the longitudinal emittance is large enough to screw you up later on. So don't neglect earlier processes, right? So did the booster to AGS transfer go okay? You can always turn off the RF and see if capture gets any better, right? If you suspect the RF is the problem, you can inject coasting beam. we mentioned this, so the wall current monitor is a really nice diagnostic in the AGS mountain ranges to check injection matching and the merge. There's a learning curve to setting up the bunch merging, to setting up the mountain range. So again, totally non-invasive. I encourage you to MCR3, find the hardwired signal for the wall current monitor, and go through the setups for the mountain range. And for AGS extraction, which, just to tie into this, would show you what, that the bunch merge didn't go well because of these baby bunches. Right, and if you wanted to look at the merge proper, the only way to look at it is with the mountain range. Right, protons, things are easy longitudinally. So if you're not accelerating, there are a whole slew of things that inhibit the AGS RF, right? This is one of the places where having a checklist in your head is usually useful. So the trigger could be off, right? The AGS RF enables is AGS RF triggers for some insidious reason, probably somebody messing around, right, helping you. There's the RF inhibit button. There's the early turn off button, which can be especially insidious, right? So that button inhibits the RF at whenever the early turn off trigger is set to turn it off, right? For protons in particular, we very often set that to be on the flat top for reasons related to the IPM. So the beam survives perfectly well as a flat top, right? We're usually accustomed to hitting early turn off and seeing the beam die somewhere off the acceleration ramp, right? The RF will turn off, acceleration won't happen anymore, the ramp continues and the beam dies. So that's how we use it. But for protons, we typically set the early turn off to the flat top. So it won't die, it'll just debug. And if you try to extract, the extraction system is perfectly happy to try it for you. And it will kick, and you might even see things on downstream instrumentation because you just extract a tiny little thing, like whatever fits on the G10 kicker, right? So you extract a bunch, right, a chopped piece of beam down. So it has an edge, the instrumentation might even be able to see it, but the beam is completely debunked. That also happens to the polarimeter a lot, right? The polarimeter requires bunch beam, the fixed polarization measurement, and the bananas, instead of bananas, which is completely covered in dots, and that almost certainly means you have to bunch beam. So the RF cavity can trip. You look at the Allen-Bradley panel on MCR1. Remember L10, so I should have a picture actually of the panel. L10 is not in the rows with the rest of them, right? They're 11, it's a row 5, with another red light on the end to screw you up, right? That says MCR, it's not cotton cavity, a row of 5, and then L10 on the bottom. And frequently we forget to check the bottom number, right? We just see 2 full rows of red lights and say everything's okay. So cavity voltage dropping out, we mentioned this before. The cavity hasn't tripped, it just can't sustain a voltage. So sometimes you can get it back by lowering the voltage slightly. But polarized protons in particular require as much voltage as we have. So typically they require 9 out of the 11 total available cavities. One of them is set to H equals 4, so 9 out of 10. So there's not a whole lot we can do to tune around for polarized protons. So you can lower the voltage and see if you get through max V dot, but that's typically just a diagnostic, right? Because the efficiency is probably pretty bad. Right, and then there's the AGS permit, right? This inhibits the RF, right? The idea being that we wouldn't want, if something has gone wrong, we don't want the beam to be as low energy as possible. So you can inject and you'll see all the beam die. That should have an alarm, but something to check. The most frequent killers of the AGS permit are the UVW permit, right? You've done something upstream that pulls the UVW input to the AGS, which disallows beaming the AGS, or the AGS cold snake permit, right? We're trying to limit losses on the cold snake, and it is the place of likely loss if something goes bad in the AGS and injection, for instance. And so the permit can be, you can look at all the permit inputs on this page and clear the permit from that page. So this is sort of a rundown of, now we're getting into the sort of rich model where we talk about orbits, tunes, and chromaticities, right? So for polarized, for gold, this is less of an issue because things are less sensitive in the region of tune space that we're running at. For protons, it's more important. The tune is, like we've been saying, close to 9, so small changes in the tune then make for large changes in the orbit. Similarly, because the tune is close to 9, small changes in steering lead to large changes in the orbit, and so both of those need to be monitored. And we've discussed this in ways. There are things that, there's a list of things that you can look at relatively quickly, common problems that crop up in polarized protons that we'll talk about when closer to the run. We'll talk about this in more detail. As I said, early acceleration problems can often be traced to bad injection from the booster. Right? You can increase the emittance in any of the dimensions, really. so badly, then acceleration will suffer. So if you can't find anything wrong at the point of loss, you may backtrack and look at AGS injection. The analog signal for the radial average, so this can be a little bit confusing. There are two signals. There's the radial steering signal, which is what we're sending down, right? That's the radial steering function that it thinks we asked for. And then there's a radial average. You can look at the signal from those two pickups that we talked about earlier, the radial pickups. You can look at the average signal of those. And if that, typically the sign of failure there is that it just walks away, right? It pays no attention to the radial steering function at some point, and it just walks off in one direction or the other. You can verify that by then looking at the orbit at that time and see exactly what's going on, and you can see the orbit march away. And then you probably have an RF problem. Typically it happens if synchro has gone bad. This is more of a problem closer to the flat top. Synchro is engaging too early or not doing what it's supposed to, or RIC isn't in the right state, so the synchro target is wrong. We'll talk about that all more during the AGS extraction talk. Another place the radius can go awry is early acceleration, right? If the feedback loops, if the radial loop isn't working, then as you start to accelerate, the beam will spiral inwards and the signal will walk off just with the main magnet field. And similarly, you can get all the high voltage functions. And so in addition to the voltage functions, so those functions are the amplitude of the RF in each of the cavities. There's also an RF sweep function, which is the vector sum, right? The total amount of kick the beam gets. And that looks more like a sine wave rather than just the amplitude as a function of time. And you can measure the RF frequency with that, right? There's a frequency analyzer at MCR4. Again, non-invasive and useful. I encourage you to set that up and measure the frequencies at injection and extraction, for instance. This is the same picture from yesterday. This one over here. More useful if the talk from yesterday happened 6 weeks ago. So this was the booster extraction AGS injection process. These are the functions I was just talking about. I'd like to see one where there's failure. So this is the AGS main magnet. This is the radial steering function, the radial average function, and these must be injections. Transition losses, as I said, you can check all the triggering, right? You can see that the gamma quads are firing. The phase error, assuming there's beam surviving and you're just losing part of it, will show you that when the RF thinks transition is happening. So it's when it's doing the phase jump. Whether that's at the time the beam is going through transition is another matter. That's more an issue with setup, I think. Typically, the problem with transition is that one of the quads will trip, one of the gamma quads will trip. That's worse than having none of them trip. Because remember we were talking about how they cancel out pairwise. So when one of them trips, you typically see a notch loss in the beam at transition. And it's usually easy to diagnose because it's tripped completely and there's an alarm on the screen for you. If that's going to take a long time to fix, for instance, you can push the transition triggering way off the end of the cycle so that the power supply guy can do diagnosis and not do the gamma jump, right? And still, beam will likely survive. The emittances will be less than desirable, well, more than desirable, because you're going through transition slowly, but you may actually survive transition. So tripped gamma quads, one of the gamma quads not firing at the correct time. So all the gamma quads not firing at the right time is probably a setup issue. If one of them is significantly mistimed, you probably have a control issue or something like that. And as I mentioned, this is a Gauss event, and you can look at whether the events are even coming out, right? There's this program called event link display, where you can see cycle by cycle whether events are coming out. It can be very useful if you think you have a timing issue or a control issue rather than an issue with the power supply. And this says incorrect tune with polarized protons is typically, right? The tunes are incorrect, right? Polarized protons requires incorrect tunes, so the problem is typically the tune has drifted away from whatever we've set up to run at. The tune is more stable than the orbit. So if I were diagnosing losses on the AGS ramp, I suspected that it was transverse dynamics, I would start with the orbit and see what I got there, compare it to an old set that I knew was correct, that I knew we ran well with, and if that looked okay, then I would move to the tune. I did notice that this morning I was going through this talk. I don't mention that the AGS tune meter. I think the first time this talk was written, there was no AGS tune meter application, and it was relatively difficult to measure the AGS tune. It's actually quite nice now to measure. It's very similar to measuring the tune rect. So there's an AGS tune meter application, and you can measure the tune in an arbitrary time of the cycle. And that's obviously useful as a diagnostic, particularly for polarized protons, where tune control needs to be on the order of 10 to the minus 3 or so at some point in the cycle. Late losses, right, as you roll over onto the flat top, the extraction bumps typically we try to extract as soon as possible after we come to flat top. So sometimes the extraction bumps are coming on too early or not firing and we've tuned up for them being on. Also, typically a setup problem if timing is too early, synchro engaging too early, extraction bumps coming on too early. An extraction problem can actually look like a late acceleration problem because we sandwich it in as tightly as possible for both gold and protons in particular because we take polarization measurements on the flat top. And the longer you can take polarization measurements per cycle, the less time you can take per measurement. So I've laced this throughout the talk for the most part, but and we'll talk in greater depth about polarized proton operation later. These are things of special concern for polarized protons, right? We make things difficult on ourselves for the purposes of maintaining polarization. So we put the tune where, ciphers would tell you not to put it near the integer. You need good closed orbit control. This tends to drift it right through. During the run, maintaining polarization will be largely tuning those harmonics that we talked about. Vertical sine and cosine 9 will drift sometimes over the course of a shift, sometimes over the course of days. That is typically what needs TLC for polarized protons. And so it would be where you went first if the polarization were bad or if transmission got bad, which it will almost always be, right? If you sit during a 6-hour polarized proton store and then come back, I would be very surprised if transmission and polarization were exactly where they should be, transmission in particular. It's just something to know that in this process of being ready for the next fill, right, somebody on the shift should really be ready to man the AGS, particularly for the overnight shift where the AGS guide flow has been working on the whole time. So it's an additional thing that we have to worry about in addition to all the polarization measurements and all the other things we have to do. And like I said, polarized protons requires more total voltage from the RF, and we typically run very close to the limit of what we need. And so early acceleration losses can very often be RF just being a tiny bit low. Right, so any questions?
When doing a harmonic manipulation, is that done with dipole?
That's entirely, okay, which harmonics are we talking about? The answer is it depends.
When you're, the ninth order.
This sine 9 theta, so when we were looking at AGS over display?
Yeah.
Right, we're talking entirely about steering, entirely about the low field orbit correctors. And that's what we're steering with. Most of the bumps that we talked about, the snake bump, and yesterday the injection bump, and tomorrow the extraction bump, those are all backlink windings on main dipoles. But when we're talking about, tuning orbit harmonics, we're talking about the low field. These little guys, 4 per supercycle.
And that,
Super period. Thank you.
and that changes the amplitude with respect to the harmonics, right? Is that how it works? Or is it the other way around?
So we put kicks in, all right. So the current in each one of the dipoles is, like I said, is proportional to whatever harmonic you're tuning. So if we say we're tuning sine 9 theta, right, the current in each dipole is some amplitude, whatever amplitude you ask for, half an amp, times sine 9 theta, where theta in this case is, so this is the AGS, right, and this is A1, bad location for A1, right, and this is A1, right, then this is theta, it's just geometric, right, so the correctors at, I wasn't on the, so in each one of the correctors we put in a kick, some of them are up, some of them are down, and if we just plot them right, you could draw sine 9 theta all the way around. So the current in each one is determined by this angle and the amplitude that you ask for. Right, and that provokes a response in the orbit that has the same characteristic, the sine wave or cosine wave with nine cycles in it per transit around.
And those in phase, just like what you've done with the current. So you're doing a driven, you're doing a driven harmonic oscillation. You're driving the oscillation and it stays in phase with not really any more complicated than that, but I understand it's about the word.
And in general, there are harmonics because it's a multi-particle structure.
No, one particle going around, right?
But if there, one thing, if there was one particle, there would be, the harmonic would be the tune. There would be a tune effect. I don't understand that, but.
Just a bunch of words. All right, Benson, go to it.
Okay, so the measured orbit, I think I know what you're talking about. So what you're looking at in AGS orbit control, right? I'm never gonna get there. I'm gonna hit the thing.
I'm just thinking in general, what the definition of harmonic sounds.
Okay.
And, you have some way you come in and decompose the different frequencies and.
Right, and this is what we're talking about, right? This is
Yeah.
the wave that we're decomposing into different frequencies. So what you're looking at here is the measured orbit averaged over many turns. Right, so when we acquire an orbit, the pickup looks at the beam over many turns, right? And because we're not kicking the beam and we're not doing anything funny, typically the average position of the beam doesn't change much turn to turn. So we average the same thing many, many times. So you're right in that because there are many particles, the closed orbit is the same every, right? The measured orbit is the same on every turn, right? Because they're all oscillating around this, but the net, the average position doesn't change much. If you have one particle and could measure the one particle, right, it would change by the tune, right? The pickup would, exactly, it would see the tune, right? You measure just the way Rick injection looks, right? X as a function of turn. Right? If I measured one particle, there'd be no damping, and I just measure, I just measure its position on every turn, right? And the frequency of this is exactly the tune. You're right. But what I'm doing here is averaging over all these turns, right? So this would give me 0. The thing I got at this pickup, at this location, would be 0. Right, in this picture, and for some offset, I would get this. And so what I measure with the pickup is the average here, right? And I just measure that at every individual location. Right. So the individual pickups could, in principle, see the tune, right? If you had, that's how the tune meter works, right? There's a pickup, we kick the beam, and it sees just this, right? Because now I'm moving the centroid, it oscillates at the tune. So I can measure the tune with a single pickup because of, I think, what you said. But the harmonic as a function of position in the ring is a function of all the dipole errors that we have and the tune. That kind of an answer. That's why I was throwing a bunch of words. But.
I'll have to look into that.
Right. I mean, if you get this, if you get the difference between this picture and this picture, it's helpful, right? To sort how you think of closed orbit from how you think of this turn-by-turn stuff. Which once you see it is kind of easy, and before that it looks like a mess.
And if this is looking like ninth harmonic, this makes it worse. I mean,
yeah.
This picture could be no ninth harmonic at all. We could, like the extraction bump, well, even the extraction bump sort of has a look of ninth harmonic about it, but we're always dominated by the error of the equilibrium orbit. The equilibrium orbit, which is, this is a plot of the equilibrium orbit. The concept of what is an equilibrium orbit is a very important concept. And that's, I can do that, I can talk about one particle, and if I put it on the equilibrium orbit, which is just to say, I send that particle, and when I watch it come around again, it isn't oscillating. It's exactly where it was before. So you've lost the tune information. You've given it away because you're sending this particle on the equilibrium orbit. And what this application is showing you is what that equilibrium orbit would be doing. So it doesn't seem like the tune information would be in your face. Unfortunately, it is because of this connection between errors in the machine and the running the tune. Well, the errors in the machine always get turned into having a dominant term which is close to the harmonic closest to the tune. Right, it still went worse, and going from worse to the other thing is hard.
Any other questions?
Just have one.
Okay.
Brian,
Would the snake dipoles be?
Brian, could you speak up?
Oh,
Or not
okay.
recording. Speak up loud.
When the snake current reaches its DC value, and you showed there was the beginning of a function, I don't know what it was, but the snake correct program, you showed that the function was something in the beginning.
Right.
Are those the snake correctors that are changing there?
Yes.
Right.
But it's
So-
not the snake itself?
No, like I said, the snake itself is completely DC, right? All through the cycle, between cycles, it just sits at one current, one field, the entire time. But its effect on the beam, right? We don't want the quads on. Ignore that. The effect on the beam dies away very quickly with rigidity, with energy of the beam, right? So for injection, we need quite a bit of current. This is 100 amps, for instance. And then they drop away very quickly as soon as the main magnet takes off. So we need to compensate for the snakes at low energy, and then as the energy goes up, we don't need any more compensation. But the snakes are still on, right? Their effect on the spin stays the same, but their effect on the optics drops off. And so we don't need to